It's tackling all right, diving into something pretty fascinating today. MrT5. It's not just another language model.
Right.
It's tackling a core problem.
Mm.
We see a lot. Efficiency.
Yeah.
We've got the original research paper right here.
Great.
And just from glancing at it, this could change how we think about language models entirely.
Yeah, definitely.
We always hear about, computing power being the big hurdle, but the real hidden cost is per token.
Yeah.
Those chunks of language that models work with.
Right.
And surprise, surprise, not all languages are created equal in the token world.
Exactly.
Some languages need a ton more tokens just to convey the same information.
It's true. It's like some languages are paying a premium just for existing in the digital space.
Bro.
The MrT5 paper actually highlights how this can create real economic disparity.
Wow.
Especially when you factor in API costs.
So certain languages are inherently more expensive to process?
Pretty much.
Yeah. That's a bit unsettling.
It is.
Yeah.
It's
but what's the root of this problem?
Well,
the paper keeps mentioning this term subword tokenization. Is that the culprit?
Subword tokenization is a very common way to break down language for these models.
Okay.
Think of it like chopping vegetables for a recipe.
Okay.
You wouldn't chop everything the same way, right?
Right.
Some ingredients need a fine dice.
Sure.
Others are better left in larger chunks.
Okay, so subwords are like those chopped up bits of language.
Exactly.
Okay.
But the problem is this chopping can be inconsistent and lead to some serious issues.
Okay.
The paper outlines 3 major downsides.
Okay.
Sensitivity to errors.
Bro.
Inconsistent compression across languages, and problems with handling numbers.
Okay, let's unpack those.
Sure.
What do you mean by sensitivity to errors?
Well, imagine that recipe calls for 1 teaspoon of salt.
Okay.
But you accidentally type 1 teaspoon?
Oh.
Suddenly the dish might be completely ruined.
Yeah.
That's what can happen with subword tokenization. A single typo can throw the entire model off.
Wow.
Because those subword boundaries get messed up.
So these models are surprisingly fragile.
They can be, yeah.
That seems like a big problem if we're relying on them for, important tasks.
Yeah, for sure. It is. And then there's the compression issue.
Right.
Like we mentioned, some languages require way more tokens than others to represent the same information.
Right.
This makes them costlier in terms of processing power and ultimately money.
That's where that economic disparity comes in.
Exactly.
Almost like a digital language tax.
Yeah, kind of.
What about the problem with numbers?
Yeah.
How does subwords mess that up?
Numbers can be tricky because they often need to be treated as a whole unit.
Right.
But if a model is only seeing subword chunks, it can struggle to perform even basic calculations.
Really?
Yeah, it's like trying to do math with only fractions of the numbers.
Oh, wow. Okay, I'm starting to see why the researchers went looking for a different approach.
Yeah, it makes sense.
But what's the alternative?
Well,
is there a better way to chop up language for these models?
There is, and it's called byte-level modeling.
Okay.
Instead of using subwords, these models break things down to the level of individual characters.
Wow.
Or even bytes.
Huh.
It's like going from chopping vegetables to working with individual grains of salt or pepper flakes.
That sounds incredibly precise.
It is. It's very fine-grained.
Does that solve all the problems we've been talking about?
It addresses the subword issues.
Okay.
But it introduces a new challenge. Extremely long sequences. Oh. Remember those tiny pieces of salt and pepper?
Yeah.
Now imagine a recipe stretching on for pages and pages.
Oh my gosh.
Byte-5 is a good example of this.
Okay.
It achieved impressive results, but it was incredibly slow because it had to process these massive sequences.
So we've traded one problem for another?
Kind of, yeah.
That's hardly a solution.
That's where MrT5 comes in.
Okay.
It takes the best of both worlds. It's still a byte-level model. Okay.
But it has this fascinating ability to merge information.
Merge information. How does that work? Are we just randomly deleting stuff?
Not at all. It's a much more intelligent process than that.
Okay.
MrT5 uses a mechanism called a delete gate, which learns to identify which parts of the sequence are essential.
Okay.
And which can be safely combined without losing crucial meaning.
So it's not just blindly shrinking things. It's actually understanding what it can and can't condense.
Exactly.
Yeah.
Imagine summarizing a book.
Okay.
You'd keep the key plot points.
Right.
But condensed descriptive passages or less important dialogue, right?
Yeah. Yeah.
That's kind of what MrT5 is doing.
Interesting.
Is learning to speed read those incredibly long byte-level sequences.
This delete gate sounds like the key innovation here.
It's a big part of it, yeah.
How do they actually get the model to learn which information to merge?
Right.
That seems pretty complex.
It is. It's pretty clever, actually.
Mm-hmm.
They use a combination of soft and hard deletion. Okay.
During training.
Soft and hard deletion.
Yeah.
Okay. What is that?
Think of soft dilution like a dimmer switch.
Okay.
It reduces the importance of certain bytes without completely removing them.
Okay.
This allows the model to still learn effectively through a process called backpropagation.
Hold on. Backpropagation. Let's back up for a second.
Sure.
What exactly is that, and why is it important here?
So backpropagation is essentially how a neural network learns.
Okay.
It's a way of adjusting the model's internal connections based on feedback.
Got it.
Think of it like teaching a dog a trick.
Okay.
You reward it when it gets it right.
Right.
And that feedback helps it learn.
Yeah.
Soft deletion allows the model to receive that feedback.
Okay.
Even as it's experimenting with merging.
Okay, so soft deletion is like giving the model some wiggle room to learn,
Yeah,
right?
exactly.
But what about hard deletion?
Yeah.
When does that come in?
Once the model is trained and ready to be used, it switches to hard deletion. This is where those dimmed down bytes get completely removed,
Right.
making the processing much faster.
So it's like the model is learning to be ruthlessly efficient.
Yeah, you could say that.
But how do they ensure it doesn't become too ruthless and start deleting crucial information?
That's a good question. That's where the researchers introduced a couple of clever mechanisms.
Okay.
A regularizer.
Okay.
And something called a P controller.
Let's break those down. What do they do?
The regularizer acts like a safety net.
Okay.
It prevents the model from getting too delete happy.
All right.
And losing vital information.
So it's like a safeguard.
Yeah.
Against overly aggressive merging.
Exactly. Think of it like making sure those key plot points from our book summary don't accidentally get tossed out.
What about this P controller?
Yeah.
That sounds even more intriguing.
The P controller dynamically adjusts the dilution rate based on the task's difficulty. It's like having an autopilot for that merging process.
Okay.
Constantly tweaking the settings.
Right.
To ensure a perfect balance between conciseness and accuracy.
Okay, I'm starting to see how all these pieces fit together.
Good.
This delete gate,
the
soft and hard deletion, the regularizer and the P controller, it's all working together to make this merging process as intelligent and efficient as possible.
It is a very elegant solution, I think.
But before we go any further, did they actually test whether this merging business really works?
Oh, yeah.
Like, does MrT5 actually understand what it's deleting?
They did. And the results are quite remarkable.
Okay.
They ran a series of diagnostic tests. Tasks like removing vowels or merging specific character sequences.
Interesting.
And what they found was that MrT5 wasn't just blindly dropping tokens.
Okay.
It was learning sophisticated patterns aligned with each task.
Wow.
It was almost like it had figured out the rules of the game and was playing strategically.
So it's not just a brute force approach.
Nope.
But it's actually demonstrating some level of comprehension about the language itself.
Exactly. The results show that MrT5 is processing information, identifying patterns and making decisions based on those patterns.
That's pretty incredible.
It's a huge step beyond simply shrinking the input size. It's about intelligent compression.
All right, I'm definitely intrigued.
Good.
But we've only scratched the surface of what MrT5 can do right.
We have. There's a lot more to explore.
We still need to talk about how it actually performs on real-world tasks.
That's the real test.
Yeah.
And that's what we'll delve into next.
All right, I'm excited for that.
Me too.
Let's take a quick break, and then we'll dive into those real-world results.
Sounds good.
So we left off talking about, this idea that MrT5 isn't just about making things smaller, but about making them smarter. But how does that actually play out when you throw, real-world tasks at it?
Yeah, good question.
The paper mentions something called continued pre-training. What's that all about?
So think of pre-training as the foundation of a language model.
Right.
It's where the model learns the basic patterns of language from massive amounts of text data.
Okay.
The standard approach is called span corruption, where you randomly mask out chunks of text and train the model to predict what's missing.
So it's like giving the model a giant puzzle with missing pieces.
Exactly.
And seeing if it can fill them in based on the surrounding context.
Exactly. And the researchers wanted to see how MrT5 would handle this kind of large-scale learning. They trained it on both English text and a massive multilingual data set called MC4.
Wow.
This data set covers a huge range of languages. So it's a real test of the model's ability to learn efficient merging patterns across different linguistic structures.
That sounds incredibly challenging.
It is. It's a big task.
How did MrT5 fare against the competition?
So they compared it to Byte-level, that Byte-level model we talked about earlier, as well as some other methods that used random or fixed token deletion. And the results were quite impressive. MrT5 consistently outperformed the baselines. It achieved lower loss on the span corruption task while significantly reducing the sequence length.
So it's learning those efficient merging patterns without sacrificing accuracy.
That's right.
It's a big deal, right?
It is. It shows that MrT5 isn't just compressing information. It's doing it intelligently, preserving the meaning while streamlining the process.
Okay, so it aced the pre-training phase.
It did,
But how about those real-world applications? Did they test MrT5 on tasks that actually matter?
They did. They focused on two main areas. Cross-lingual natural language inference and character-level tasks.
Okay, I'm going to need you to break those down for me.
Sure.
What exactly are those?
So cross-lingual natural language inference, or XNLI for short, is about understanding relationships between sentences across languages. Can the model tell if two sentences in different languages mean the same thing, contradict each other, or are completely unrelated?
So it's like a high-stakes game of linguistic matchmaker.
You could say that, yeah. It's about making connections.
Why was this a good test for MrT5?
Because XNLI typically involves long input sequences, which is where those traditional byte-level models really struggle. Remember, longer sequences means slower processing times. But MrT5, with its merging superpower, was able to handle those long sequences much more efficiently.
I'm guessing the results were good?
MrT5 achieved comparable, and in some cases even better accuracy than Byte-level, but with significantly faster inference times. We're talking about a 38% speed up.
Wow, that's significant.
Yeah.
On the English XNLI test set.
It's a big improvement.
Okay, that's a pretty substantial improvement.
It is.
What about those character level tasks? What were those all about?
Those tasks were designed to see if MrT5 could handle the nitty-gritty details of language, use spelling correction, and word search as benchmarks.
So even though it's become this, master of merging, it hasn't lost its ability to sweat the small stuff.
Exactly. It can still handle the fine-grained details. And once again, MrT5 excelled. It maintained accuracy comparable to Byte-level on both tasks. While significantly reducing the sequence length and speeding up the inference time.
So it's faster, more efficient, and just as accurate.
It seems to be.
Sounds like a win-win-win situation.
It does. It's very promising.
It really does. And the implications of this are huge.
They are.
Especially when you consider, the growing demand for multilingual NLP applications.
Exactly. This is where it gets really exciting.
All right, let's talk about that. We've established that MrT5 is a bit of a rock star when it comes to performance.
It's definitely impressive.
But what does this all mean for the future of language modeling?
Right.